I'm going to cover two things. I want to talk about diverging lenses, and I also want to talk about something called the lens maker equation. Okay, diverging lenses are lenses that are thinner in the middle. Okay. So they're always thinner in the middle, and they have a negative focal length. A diverging lens is often called a negative lens. So I kind of think there being a parallel between a concave mirror and a converging lens, because both of those have positive focal lengths, and then a convex mirror and a diverging lens, because both of those have negative focal lengths. Again, we can draw pictures of a variety of shapes. That would be a double concave. If it's flat on one side, that's a plano concave. And it can also be a meniscus where both surfaces are curved. But you'll see how this side is flatter than that, so it's still, that is a meniscus. Okay, so that's what some of them might look like in terms of shape. Let's look at how the rays behave, or how images get formed. If I have a double, the easiest one, let's do diverging, let's just do a double concave. It will have two focal points. They call this one F1 and this one F2. That bothers me a little bit, but that's how they're labeled. If you have parallel rays that are coming in, let's draw that imaginary line. So here's some rays that are parallel to that axis coming in. They will actually diverge as if they came from this focal point. So you can easily see why they get the name of a diverging lens. They appear, if you were over here looking at it, you would think they were coming from back here. If we had a whole bunch, we had the sun over here with a lot of parallel rays and we looked through it, our eyes would focus back and we'd actually see an image of the sun right there at that focal point. If the rays, however, let's look at the other possibility. Again, here's F2. Here's F1. Now, focal lengths are determined a little bit differently with converging and diverging lenses, and we're going to look at that very next thing. These radius of curvatures, one of them can be flat, one of them can be curved. It doesn't matter. There's only one focal length. Okay. So our second rule for image formation is that any rays that are headed directly towards this focal point, oops, let's use a color for that. If I have a ray that was headed, there it is, it's headed directly towards this focal point, it will refract in such a way that it goes parallel. Okay. So here's another one. It looks like it's headed straight towards this focal point, but when it gets here, it refracts so that it's going parallel. So either way, you can see how it's spreading the rays apart. These were parallel, they're moving apart. These look like they were going to actually converge to a point, but again, they got moved apart. Okay, so that's how the ray formation works. I don't have a problem but we could make one up, but I don't think you'll have any trouble. The only thing you need to remember is if you have a diverging lens, your focal length is negative. Okay, that should take care of diverging lenses. The final big idea that I want to talk about in this segment is something called either the thin lens equation or the lens maker equation. I think when I first learned it, we called it the lens maker's equation. Your textbook uses this one first and then uses the other one. But it's used to determine the focal length of a thin lens. And it says that 1 over the focal length is equal to n minus 1 over R1 minus 1 over R2. Okay? We of course know that F is the focal length. N, of course, is the index of refraction. We haven't really talked about that in a while. But we know that the higher the index of refraction, the more the rays get bent. When you get sunglasses, when you get prescription eyeglasses, depending on your age and your vision issues and what type of frames you're going to pick, you may get the regular lower index of refraction lenses, or you can get the ones like mine. These are what they call high index lenses. High index lenses allow them to use a thinner lens to accomplish the same thing. And so since I get the ones that don't really have a frame, they just have the little screws, they try to keep the lens as thin as possible, and it makes it really lightweight. But you have to pay a little extra to get that higher index of refraction, okay? The R1 is going to be the radius of curvature of the first surface. So the radius of the first surface, and R2 is the radius of the second surface. Okay, we've already mentioned it, but there is a rule for deciding whether or not R is going to be positive or negative. It needs to be on the side of the outgoing light in order to be positive. So the center of curvature is on the side of outgoing light when R is positive or greater than 0. Okay. If it's on the side of the incoming light, then the center of curvature is on the negative side, incoming light, the radius of curvature is going to be negative. Let's look at a very specific example. Take just a minute, but you can pause this and write down all this information. Okay, let's suppose we have a lens that looks like this. It's flat on one side, it's convex on the other. We know that when we get finished with this problem, this better have a positive focal length because it's a converging lens. So this is R1, and it equals 10 centimeters. Okay. And this is R2. And anytime you have a flat surface, it equals infinity. The radius, it would have to have an infinitely long radius to be completely flat, okay? Notice, let's look at the signs. If I were to draw the axis, the center of the curvature for this surface, this curve, is over here. Well, this side we normally think of incoming, this side we think is out. So, since the center of curvature is on this side, that's going to be positive. Okay, we'll look at one where it's negative in just a minute. Let's assume that the index of refraction for this is 1.50. So we're going to get 1 over f, 1.5 minus 1. R1 is positive, so it's 1/10 minus R2 is infinity. Well, the nice thing is 1 over infinity is simply 0. So I know what to do with it. That's going to be 0. So this is going to be 0.5 times 1/10 is 1 over f. That gives me 1 over f is 0.05. If I take the reciprocal, I get f equals 20 centimeters. It's good. It gave me a very expected result. I expected to get a positive focal length. Okay? Let's try a different lens and let's pay attention to which one's positive, which one's negative, and see if we can get the right answer. Still lens. Let's let R1 have a radius of curvature of 10 centimeters. And let's let R2 have a radius of curvature, it's a little flatter, of 15 centimeters. Okay, now let's think about that. The center of curvature for R1 would be over on this side. Well, that's incoming light, so I know that R1 is going to be negative. So for this problem, when I plug it in, R1 is going to be negative 10 centimeters. But the center of curvature on this side would be over here. Picture the circle. It has a center over here somewhere. So R2 would be positive 15 centimeters. Let's assume we have the same type of glass. We have an index of refraction of 1.5. So when I put that in, it's going to be 1.5 minus 1 over negative 10 minus 1 over positive 15. Notice this quantity is clearly going to be a negative quantity, so we're definitely going to get a negative focal length. That's 1 over f. That's going to be 0.5. The common denominator here is 30. That's going to be negative 3/30 minus 2/30. That's going to be negative 5 over 30. Or I can just do it on a calculator. And then I'll take a reciprocal. Let's see. Double check. 1 divided by negative 10 minus 1 divided by negative 15. Let's make it a fraction. See if I did that right. Yep. Oh, what? I did not do that right. Oh, no. Didn't do it on my calculator. 1 divided by negative 10 minus 1 divided by 15. Make that a fraction. That's negative 1/6. I could have reduced it. Negative 1/6 times 0.5. And then take the reciprocal. And F came out to be negative 12.0 centimeters. Okay? The formula is easy. Just pay attention to the radius of curvature. This is incoming. If the center of this curvature is over here, is going to have a negative value. If the center of curvature is over here, it is going to have a positive value, and that will get you through. And you should know what to expect. When you look at the picture, if it's thinner, we know it should come out to be negative because it's a negative lens or a diverging lens. Okay, I think you get enough practice with this on Mastering Physics, but if you have any questions, by all means email me or show up for a collaborating meeting Monday and Wednesday at 9 in the morning. That's it for today.